Yeah, good morning, madam.
Good morning.
I welcome you for the last day of this FDP and the first session as well of this today. And for you, it is the second session.
Yeah.
I welcome all the participants for the last day of this FDP and second session by Dr. Shobha Bagai. So she'll be delivering a talk on application of Keller box method to nanofluid, part 2 with us. I request Professor to just continue.
Thank you so much. Thank you once again. Yesterday, in fact, in my last session, we talked about we gave an introduction to the Keller box method. And in this session, we look at the application of that same numerical methods, in particular to a nanofluid flow. So, in fact, before we start with the application of the Keller box method to the nanofluid flow, let's try to quickly understand what are these nanofluids and why the need, arose, for the nanofluids. In fact, when we talk about problems in fluid dynamics, so heat transfer is one of the, a major problem that is studied by researchers across the globe. It finds its application in a number of places, and of course, one of them is cooling. So cooling is in fact, one of a very, very important need of the different industrial technologies, because what happens is that when we use these technologies, we use the machinery. So what happens is the heat is generated, both, in terms of your micro level, which, you can take it as your computer chips, your laptops, your mobile phones. So you will see that what happens is that, because of the excess usage, your instrument, it does become heated. And also at the macro level could be, your transports, your machinery that are being used in the industries. So, for cooling, in fact, there has been base fluids which have been used. And these fluids are used to, transport or the transfer or distribute the heat. And these fluids, in fact, conventionally has been your air, your water, or you can take it, as your organic fluids, which is ethylene, glycol, and oil. Now, we all are aware that the thermal conductivity of any fluid is very, very small as compared to the solids. So naturally, what happens is the transfer of heat that happens at a very, very slow rate. In fact, almost, a century ago, which was in the beginning of the last century, Maxwell, he did develop a theoretical model for enhancing the poor conductivity of the liquids by adding certain solid particles to them. And these solid particles were basically small metallic particles. And, since these metallic particles, if they are introduced into the fluids, now because of the high thermal conductivity of metals, Maxwell argued that this can improve the efficiency, of the heat transfer if you have a heterogeneous fluid being used in such a cases. So, of course, once Maxwell, he proposed his theoretical report. So, the researchers, they started doing experimentation, right? Developing models, that can we have a model where instead of just simple base fluid, we now have a mixture which consists of your solid particles and liquids. Now we are talking about the earlier 20th century. This was somewhere around 1930. So at that time, the particles that were taken, which were mixed in the base fluid, they were basically, a small sized millimeter or at the most a macrometer size particles. So micrometer, if you understand, they are of the order of 10 power minus 6 meters. But, once when they were being applied to the actual problem, so there were certain issues that arose in that case. The first thing was that, as compared to the fluid molecules, the size of these particles were big. And then what happened is because, of their mass, they settle down very quickly at the base. So instead of having a homogeneous, mixture, so you did have a layer of these solid particles and a layer of the base fluids. Now, if you are doing this study in case of the porous medium, then what happened was that the pores, they were in fact clogged by these the small microparticles, the small micro solid particles that was introduced into the fluid. And in order to actually have a significant effect on the efficiency, on the amount of the thermal conductivity of this suspension, the concentration of these particles, had to be very, very high. So, if you need to have a high concentration, that means you needed to have the proportion or the ratio of the solid particles large. But then, they would clog the pores if you're doing it in a porous medium, or they would settle down, not forming a homogeneous mixture. So these problems, they certainly were there, and at certain time, this concept that the thermal conductivity of a liquid can be increased by adding, your solid particles to the fluid, that took a backseat. So, but what happened was that now with the modern technologies coming up, so we have this nanotechnology coming, and because of the nanotechnology, it is now possible to have particles which are of the size of your nanometers, right? So nanometers is basically 10 to the power of -9 meters. So since the modern technology now enables us to have particles, which are smaller in size. So if they are smaller in size, so these kinds of difficulties which arose with the microparticles, which Maxwell had proposed, those difficulties could be overcome because the mixture could now be a little homogeneous, and nanoparticles being very, very small, they could float in the base liquid rather than settling down. And these nanoparticles, they have these superior properties, whether it be mechanical, whether it be optical, electrical, magnetic, thermal properties. So because there are different kinds of nanoparticles that are being made right now, and we'll come to that a little later. So, all these properties, when we study the heat transfer, in fluid dynamics, the efficiency of that heat transfer could now be achieved with a theory which was proposed almost a century back by Maxwell. So, Coy, in fact, in 1995, so he was doing some research work for the defense services of the US, and he proposed, now even Coy, in fact, in 1995, in fact, in 1993, what had happened was there were scientists, who were doing experimentation. They started producing, in fact, different kinds of nanoparticles, and that research had been coming up. So Coy, in fact, in 1995, the paper was published. It was there in a book. The reference is already given to you on the screen. So, he proposed a theoretical model that, let's again revive back the theory that was proposed by Maxwell. But now, instead of using a mixture which has microparticles, why not introduce nanoparticles into the fluid? The nanoparticles in the fluids, and in fact, he termed this terminology as nanofluids. In fact, if you happen to read the research paper which is by Coy, so he mentions this over right now. These fluids in which the nanoparticles are now mixed with the base fluid, we will term it as nanofluids, and he gives it in the brackets. He abbreviates it as NF. So this was, in fact, at that instance, 1995, people, really liked this idea. They, in fact, started calling it as an innovative idea that let's now have, a nanotechnology-based heat transfer fluids, right? And that can be obtained by, mixing, in fact, your nanoparticles into the base fluids. These nanofluids, the term that was coined by Coy. So the experiments were done. It had thermal properties which were both superior to the properties of their own hosting fluids and the conventional particle fluid suspensions. So, whenever something new is introduced, the aim is always that, whatever are the conventional, the existing methods that are there, can its efficiency be increased? So, similarly, the goal of the nanofluids was in fact to achieve, whatever is the maximum possible thermal probabilities where the concentration that you have of the nanofluids is small. So I hope you understand that it's a kind of an optimization problem. You want to achieve a very, very high thermal properties of the base fluid, whereas the concentration has to be low. The concentration has to be low so that, the other properties are not disturbed. And the dispersion or this mixed solution that is obtained must be stable to host the fluid. So in order to understand that, of course, it's very, very important to understand that how does the nanoparticles enhance the energy transpose in liquids. So naturally, I will not get into the details of there, but I would certainly like to read out some excerpts from that, the founding paper which was there by Coy, which came in 1995. So nanofluids are expected. Now, just look at the grammar he's using, because, you need to try to understand this was done by him in 1995, where it was yet to be settled down that whether, the effect as what Coy has proposed will be there or not. So therefore, he uses something, as a future tense, that nanofluids are expected to exhibit superior properties when compared with conventional heat transfer fluids and fluids that contain micrometer sized metallic particles. So the micrometer sized metallic particles was the one that was proposed by Maxwell. So because the heat transfer, it takes place at the surface of the particles, so it is desirous that the surface area of the particles that are there, that should be large. And since, this had already been, the experiments had been done, it had been established that the nanoparticles have extremely large surface areas and therefore have a great potential. So again, it's in the future that, what he's mentioning out over here, have a great potential for application in heat transfer. The much larger relative surface area of the nanophase powders when compared with the conventional micrometer size powders should markedly improve the heat transfer capabilities and the stability of the suspension. So this is, what he proposed in his paper. And then, again, towards the end of the paper, he gives an example as to how he perceives, that what is the kind of an efficiency that can be achieved by considering a nanofluid rather than a conventional fluid, right? So he mentions that to improve the heat transfer by a factor of 2, that means if you just need to, double it, the pumping power with a conventional fluid should be increased by a factor of 10. However, if a nanoparticle-based fluid with a thermal conductivity of 3 times that of a conventional fluid were used in the same heat transfer equipment, the nanoparticle-based fluid would double the rate of heat transfer without an increase in the pumping power. So that means what he said, that what in the conventional way, if you needed to double the efficiency, the pumping power had to be increased, 10 times. But in case the nanofluid is being used has a thermal conductivity, which is just 3 times your conventional fluid, then in that case, with the same pumping power, you can increase the heat transfer by a rate of 2. Right. So that is the power which, what he predicted, in fact, or what, he proposed in 1995. And after that, when he of course, by the time the article came, it was 1995, but during that time, it was during, the early 90s, in fact, so 92, 93 onwards. So there were scientists, who were rapidly trying to, make these nanofluids, in fact, make the nanoparticles, in fact. So different types of nanoparticles were being made, and consequently, different kinds of nanofluids were being done. And of course, they were doing experimentation, and during the experimentation, they found out that these kinds of nanofluids did have certain unexpected thermal properties of the nanofluids. But along with, doing the experimentation, so naturally new mathematical models have to be developed, which in fact complemented, what was being found, or which, also was in the same line as what was the results obtained through experimentation. And then with these nanofluids, came the generation of smart coolants, for computers, for the nuclear reactors, because they suddenly found out that, the efficiency, of cooling down these machineries can be increased manifold if instead of using a conventional fluid, a nanofluid is being used. So, different kinds of nanoparticles and base fluids could produce many kinds of heterogeneous nanofluids. And if you look at the literature, the common kinds of the nanoparticle materials that you find are for the oxide ceramic, which is your aluminum oxide and the copper oxide, metal carbides, which is your silicon carbide, then nitrides, which are formed along with your aluminum and silicon, plain metals, which are your aluminum and copper. Non-metals, graphite, carbon nanotubes has a huge application, in fact. And then you could also have the layers, in fact, so it could be a layer of, in fact, a metal and an oxide, a metal and a carbide, and so on and so forth. And the base fluid, in fact, they are generally the water, ethylene, glycols, which were used earlier, oil. Biofluids, in fact, is again something which has just come up during the last decade that you have. There you have microbes introduced into the fluids, which try to enhance the thermal properties of the fluids. Then polymer solutions, and there are certain other kinds of the common fluids also that are being used. So, the applications of nanofluids are manifold, whether it be electronic cooling, which we looked into the previous slides, defense and space, nuclear system coolings, heat exchangers, biomedicine and biomedical applications. So, a lot of these applications are even found in your, your biosciences. Then, of course, the heat fuel cell, and there are a number of applications, that you can actually find out using these nanofluids. Magnetic fluids, again, there are different kind of the nanofluids which takes the advantage, because, you have introduced the metals into the fluids. So naturally, even their magnetic property has been enhanced. So that property is also being utilized, in fact. And as I told you before, that a lot of nanofluids is being used in biosciences, because there are certain nanoparticles which show antibacterial properties, and there are these bio nanoparticles which are now being formed. In fact, this reference, which I have mentioned on the screen. So if you really want to look into the details as to how these nanofluids are being applied into the various fields that, we have mentioned before, so you can look into this reference, in fact. So, because nanofluid, in fact, has so many applications, and it did show a very, very positive result on the heat transfer. So you'll see that, there are a number of research papers, number of publications that have come out, so from 1993 to 2022, of course, I do not have an exact number, but they have exceeded the number of 4,000. And if you look at these as just in 30 years. So that's a kind, the kind of it's a kind that the researchers have been using again and again. But if you look at most of the research papers, they are always complemented with the experimentation also if a new mathematical model is proposed. So the publications now are looking at that, is it being supported by an experimentation also or not? So different approaches have been, given by the researchers, to study the problems in nanofluids. But these approaches can basically be classified into two parts. One was given by Tiwari and Das in 2007, and the approach that they developed, it was to examine the effect, of what are the variations in thermal conductivity and the viscosity of the base fluid with the nanoparticle fractions. And these were the expressions, they used for the theory of mixture. So this was the Brinkman's expression was basically used for the viscosity, and the Maxwell-Garnett's, expression was basically used for your thermal conductivity. So this is the mu effective, means it is the effective viscosity of the nanofluid that is obtained, mu F. So the subscript F basically represents your base fluid. Similarly over here, so this actually gives you that what will be the ratio of the effective viscosity. And this is the, the ratio between the effective thermal conductivity and that of the thermal conductivity of the fluid. So that in fact includes, your thermal conductivity of the particles. So that is scripted by P, and the thermal conductivity of the fluid F. And of course, eta represents the viscosity of the fluid. The second approach, was given by Bjorno in 2006. So, he in fact gave a model which incorporated two different effects. One was of the effect due to Brownian diffusion, because now, since the particles have been increased, has been introduced into the fluid. So naturally, these particles, because of the Brownian motion, they are going to have certain kind of a movement. And of course, the thermophoresis. So the thermophoresis basically is that, that the heat is transferred either due to because of, the gradient in temperature, or it is the gradient in concentration. So now because, you also have the particles over here. So naturally, the heat transfer rate and the mass transfer rate will in fact be affected both by the temperature gradient and the concentration gradient. And those are your Sauret and the Dufour effects. So, as I mentioned that the Brownian diffusion basically results from the continuous collisions that are going to happen between the nanoparticles and the molecules of the base fluid. Whereas thermophoresis is basically that how do the particles diffuse under the effect of a temperature gradient. So now let's come to, let me first explain the problem that we are going to define. So, you have a two-dimensional transient free convection flow. So you have an axisymmetric body, right? So the coordinate system this in fact is the my body. So axisymmetric could mean, it could be a sphere, it could be a cylinder, it could also be a vertical flat plate. So the x coordinate in fact is measured along the surface of the body, and the y coordinate is perpendicular to it. So the shape, in fact, of this axisymmetric body is given by my function, which we call it as r star x. And if this is immersed in a porous medium, so you have the gravity which acts in the vertical direction. And of course, there is going to be a thermal boundary layer and also a mass boundary layer that is going to be formed, in which this effect is going to be more significant than in the ambient fluid, in fact. So the equations that govern them is equation 1 is of course your continuity equation, right? So these are under the assumption that your density variations are either very small, so there are no density variations. So the terms, which include, the derivative of rho either with respect to time t or with respect to x, those terms are neglected. Equation 2 is in fact a simplified momentum equation. So simplified in a sense means this basically has been obtained by using the bosonic approximation and considering the Darcy flow. We generally work with the non-Newtonian flow. So therefore, you will see this parameter n over here. So if n is equal to 1, we have what are called as the Newtonian flow. And if n is not equal to 1, then we have the non-Newtonian flow. So they can be either be pseudoplastic or they can be pseudoplastic, and the name has just slipped my mind, doesn't matter. The third equation basically is arises because of the conservation of energy. And the fourth equation is basically on the conservation of mass, where my phi, this small phi basically is my nanoparticle volume fraction. So, if you recall that it is actually advisable that the nanoparticle fraction is very, very small. In the previous slide, we saw till 1%. So phi represents that nanoparticle volume fraction. And of course, the other physical terms, u and v, are your velocities in the x and the y direction. Epsilon is your porosity. But we have, two different parameters coming out over here, which are your d subscript b and d subscript t. Now, these, in fact, are introduced because of the two effects that is being considered by Buongiorno, which is basically the Brownian diffusion or the Brownian motion. So, d subscript b is my Brownian motion coefficient, and d subscript t is basically my thermophoresis coefficient. So these governing equations, there are certain boundary and the initial conditions which are there. So initially it is assumed that, there is no motion. So that means the velocity components are 0 and the temperature is equal to the ambient temperature. And when T, becomes 0, so the initial temperature is the wall is basically heated, right? So you have that at y equal to 0. So y equal to 0 actually means my boundary of the surface of the the physical object that we are taking. So that is TWX. The nanoparticle volume fraction is some constant, which we consider it as YW. The y component of the velocity is 0, and as we move towards the ambient fluid. So I'm sorry, there is a typo error over here. So as y tends to infinity, so then what will happen is the temperature and the nanoparticle volume fraction, they tend to the ambient value of the temperature, and my y component of the x component of the velocity tends to 0. So that's the basic, equations. It's one of the simple form of the equations that, govern your transient heat transfer in a nanofluid. When the, you have a certain object immersed in a porous medium, and we are considering that those fluids are basically non-Newtonian fluids. So, the shape parameter of the object that is immersed in the porous medium, it's basically defined as for a plane flow. That means for if you have a vertical plate or you have a horizontal cylinder, that is one. And for axisymmetric flow, so for example, if you're considering a sphere, so you'll have to find out that what will be the Rx, if you remember, was the distance between the vertical axis to the boundary of the surface that we had. And of course, the component of G along the X direction. So X is measured along the surface of the object. So that is given by this relationship. So, if you look at the basic governing equations, so the governing equations, are highly nonlinear coupled partial differential equations, right? So, you have, of course, a very, very common way of, solving these equations is that in order to, satisfy your continuity equation, you introduce a certain stream function, so that instead of dealing with 4 equations, you are now left with dealing with the 3 equations. But if you look at all the 3 equations, so you have these variables u, t, phi coming in, all 3 of them, they are partial differential equations. So in order to simplify that, certain similarity solutions are introduced into the system. And the advantage of that is that instead of now having 2 space variables, so they can be combined together into a single variable, which we call it as the similarity variable eta, right? And now I will have only equations, that will have partial derivatives either with respect to my time variable t or with respect to my the similarity variable eta, and I can very easily call it as my space similarity variable. So, once when you introduce that, these are the kinds of the equations that you get. And of course, similarly, the initial and the boundary conditions can also be looked into. But since, we want to look at these equations as an application to the Keller box method. So, these are the final set of equations, that we get. So if you recall that, the first step in the Keller box method was that you convert the higher order equations to a system of first order equations. So, you have over here, you have one derivative with respect to f. Theta is differentiated twice. So again, these primes, they are going to denote the derivative with respect to the similarity variable eta, and for time we'll have it over here. So, you introduce these new variables, which we call it as theta 1 and omega 1. So, theta 1 is the first derivative of theta with respect to eta, and omega 1, which is the derivative of omega again with respect to eta. So, once these two new variables are introduced, the three equations, in fact, they can be written in these forms. Right. So I now have to deal with a system of five first order differential equations. They are not linear, they are non-linear. So you can see the non-linearity terms, they'll be coming over here. You have the non-linearity term coming over here, over here. So then the next step was that, you formulate your difference equations. Now the difference equations are formulated at the midpoint, of that rectangular element that you had in the mesh, right? Which is, in this case, since, the functions are now functions of eta and t. So you have j minus 1/2 and n minus half. Except in those equations which do not contain the derivative with respect to the time t, those equations, in fact, can be discretized about the point, eta j minus half tn. And these were, in fact, the different terminologies, that we had used. So theta dash basically to, again, reiterate about it, that is the derivative with respect to my space similarity variable eta. So, and you apply the central differencing wherever you are getting the derivative. And if the function does not contain a derivative, you average it out, right? So averaging it out at, it can happen at different points, because whether it is, on the mesh or it is, in the mesh, or it is on the boundary, the surfaces. And this, if you recall, was the mesh rectangle that we had taken for the Keller box method. So once, because these are non-linear systems, so in fact, you'll have to apply the Newton's linearization method. So the Newton's linearization method, again, recall that my, in this case, my n represents the iteration. Okay. So a slight thoda sa difference hai, because, otherwise it becomes a little cumbersome, but just for the sake of a notation, if I use my n as an iteration, so at n plus 1th iteration, so when I apply the Newton's linearization method, so, this is what I'll get. This is the error term. And the main aim now is to reduce the error term to 0. So again, we had seen in the last session that this will lead to a tridiagonal matrix Px equal to R, where P now contains the, its elements are now your blocks of matrices. Now, since this particular example, has a set of 5 equations, so the order of each of these block elements, AIs, BIs, and CIs, they will be of the order of 5 cross 5. And of course, X is this, R is this. Again, to reiterate, these are not a single element, but these are vectors. These will be vectors, each delta I will be a vector of order of R, 5 cross 1. And each element of R is also a vector of the order of 5 cross 1 for this particular example. Then once we have got the tridiagonal system, then we understood that it will have a unique solution if the matrix P is non-singular. So you have an LU decomposition of the matrix P, right? So where L is the lower triangular matrix with its diagonal elements as the identity matrix. So these again identity matrix for this particular example will be of the order of 5 cross 5, and then you have it as the upper triangular matrix. So since it's a diagonal system, so naturally it will, L is only going to have these two diagonal elements, and you are going to have these two diagonal elements. Rest of all the elements will be a 0. And the algorithmic way to obtain still remains the same as what we had done in the last class, the last session, that U1 will be B1. Once I know U1, then I can find out my LJs, J going from 2 to 3, and then UJ, sorry, excuse me. And then this process is done iteratively. So I can, in fact, find out all my LJs and UJs. Now, for the problem, under this example, my B1, it will have a constant element. So, I can easily find out the determinant of B1 because H, after I have fixed H, so that remains the same. And similarly for BJ, the last of these B's that we have over here, this one. This, in fact, is given in terms of, I'll just come to this, because the expression that I have to write down would have become very, very large. So just, represented it by certain expressions that, I'll just tell you what these expressions are. Some A1, some AIs, small AIs, some small BIs and small CIs, in fact, which are evaluated at small j equal to capital J. And similarly, my other AJs and BJs, so these are all the BJs where J is going to go from 2 to J minus 1, right? So these are also expressed in terms of these AIs, BIs and CIs. CJ is again a constant, where you will see that only the second row and the fourth row is non-zero, rest all the rows happen to be 0. And the, the LJs that I get, the elements in the lower triangular matrix L, which are below my principal diagonal. So that's representation is basically given as this. Now, this is a very important thing that comes out, in fact, because you see that CJ is going to have non-zero rows, the second and the fourth row, whereas LJ is going to have the 0 rows as my second and fourth. So this important, property, in fact, leads us that, I can express my LJ into CJ minus 1, where UJ, if you recall what my UJ basically was, in terms of certain vectors U and V. But before I explain the last part of this, as I said before, that B1 being a constant matrix, you can find out determinant of U1. And in this case, it comes out to be h square by 4, which is not 0. In fact, it's positive. My LJ into CJ minus 1 can now be written, as the product of UJ. My UJ matrix is this, into the transpose of the matrix Vj minus 1. Now, this is one difference now when we start, applying the Keller box method into a problem. If you recall, there was an arbitrary example, I took in the last session. In the last session, my Uj and Vj minus 1 were your basically column vectors. So they were column vectors. So when you had the multiplication of those two column vectors, what you got basically was a scalar quantity. But now this no longer remains a scalar quantity. You will have a vector of, in fact, of order 5 cross 5. Again, by the matrix determinant lemma, this is given as this. And again, the problem out of, the difference out over here is because, in the previous example that we did in the last session, this was a scalar quantity, but now this no longer remains a scalar quantity. This, in fact, will come out to be a matrix of order 2 cross 2. So I cannot have 1 out over here. I will have to replace that. So, if that is a kind of a generalization one starts forming, that depending upon what is the order of this particular matrix that you have obtained, instead of writing the scalar quantity, you have to replace it by the identity matrix of that order. So in fact, I have to, as we said before, we have to prove the non-singularity of my matrix P. P is in fact given as L into U. L being, a lower triangular matrix whose diagonal elements are your identity matrix will be non-singular. And the only thing that we have to prove that my U is now going to be a non-singular matrix. U, for each value of each value of UJs we saw that it's going to be BJ minus this, that reduces to this. So basically it is a product of two of these numbers, one is determinant of BJ and one is this. So what we have to show is, I think I missed out here again, that has to be determinant in fact. So I have to show that this is non-singular and so is the determinant of BJ not equal to 0. Again, if you recall, I had said that sometimes, because these elements of my matrices are no longer constants. So, at each value, it will have a different value. So, a priori, I may not, how do I determine that whether it will be non-singular or not? What is the choices of H and K, that we can take? These are the different values of the, the coefficients of the matrix that we took. So some of them, of course, they are constants and we do know their signs. I'm not interested in their magnitude. All I'm interested in to know that whether they will maintain a proper sign throughout the fluid flow or not. So for example, if you look at A1, A2, A3, B1, these are all constants and their signs, because they are constants, they are going to maintain their sign throughout the problem. Now, if I look at B2, now B2 in fact basically involves, a constant term, which is minus K by H. Then I have theta 1. Theta 1 was the rate of change of temperature, which was theta dash. Omega 1 was the rate of change of mass, right, which was omega dash. And I have F. F is basically my, it basically represented my streamline flow, right? Now, from the physical quantity, because the temperature, in fact, if, you recall the conditions that we use, the temperature will actually go from TW in the non-dimensional form to T infinity, and TW is taken to be greater than T infinity. So the temperature is going to reduce. Since the temperature is going to reduce, so I know that theta 1 is going to be negative, right? Theta 1 is theta dash. Theta dash basically means the rate of change of temperature. Similarly, my omega 1 basically is the rate of change of mass transfer, and that will also decrease because, it goes from some constant value of phi at the wall to phi infinity, where in fact the assumption is taken as that phi is greater than phi infinity. And similarly, my F, in fact, because, U tends to 0 as Y tends to infinity, so F is also decreasing. So, that in fact gives a very, very beautiful insight to us that whatever be the value, whatever iteration n I take, whatever is the mesh point j that I take, my B2 will always remain negative, right? And similarly, I have that, B3 also remains negative. And sometimes, I feel that's the beauty of any method that comes is that sometimes, it doesn't lead to any contradiction. So the kind of, these terms that we got, it was never that, there are terms, which could be positive or negative. So they had a very, very particular sign for this physical problems. And So if I move forward, so there were two terms, if you recall. One was your determinant of Bj. So determinant of Bj, when it is calculated, it's a 5x5 matrix. So once when you actually calculate the determinant, so you have certain numbers coming out over here. Now, fortunately for us, what happened was each of these terms that came once, the sign concentration of these terms were considered. So for each one of them, each of these terms was actually positive. So since each of the terms was always positive, so what we could conclude basically was that the determinant of Bj will always be positive. So it's not zero, right? So in fact, that's exactly what I want. It can be either positive or negative, but what we actually wanted to show was that it is not going to come out to be equal to zero. Similarly, as I said that, I had missed out the determinant, I think over there, there was a typo error. So the determinant of this comes out to be a term in the numerator and the denominator, where the denominator term, is this whole expression. So again, the numerator, if I look into, again, those signs of my terms, A1, A2, small A1, A2s and B1, B2 and C1, C2. So the numerator expression, in fact, was negative, and whereas the denominator which came out over here, that was in fact positive. So that I should have, is positive. And therefore, this determinant was negative for any choices of H. So for this particular problem, we did not get any constraint either in the step size for my space variable, which was X, or in the step size, of the time variable, which was K. And this is something, we have taken it from this paper of myself and my student, which came in the SN Applied Sciences. But there's another, if there was another problem that we considered, which was not on nanofluids. So there, we had got a constraint on H and K. So the idea of telling you all about this is that, whenever you are solving any problem, so you specifically, if you're trying to use the Keller box method, so there are two ways. One is, to take a very small value of H and K so that you do not have to check these conditions again and again. And there's the possibility that the method will work, the method will converge to the exact solution. That becomes, very, very high. The other way is if this kind of an analysis from a problem be done, and here is a word of caution to everybody, it's not always easy to do this kind of an analysis. So sometimes you can do it for a simpler problem, certain variable parameters that you are taking into your problem. So that can be taken as a constant, derive it for that, and then you do get, you can in fact have a very, very intelligent guess, that whether those H and K, the step sizes, will work or will it not work, rather than just doing a hit in the trial method. So thank you so much, for inviting me out over here, and thank you to all the participants, who would be listening to me very patiently on the YouTube channel. So thank you so much, and over to you.
Thank you, madam. Thank you very much. So very well explained about nanofluids and applications and Keller box method, madam. Thank you very much for your wonderful lecture.
Thank you so much.
Thank you very much, madam. No questions, madam. Actually, we didn't find any questions.
Okay.
Hello, madam.
Thank you very much, madam.
Hello, Dr. Neejaji. How are you?
Oh, fine, madam.
Good to see you.
Busy with your classwork also, madam.
I know that. We are also busy out over here. In fact, we are following a different, academic calendar. So one of our years are having their exams going on right now. Mm-hmm. One is having their assessments going on. The others are having their classes. So we have 3 different calendars working right now.
Yes, madam. Yes, madam. Anyway, thank you, madam. I couldn't attend, but it will be there on the YouTube, no?
Yeah, it will be there on the YouTube.
I'll go through once. I'll come back to you later, madam.
Yeah, sure.
Thank you so much, madam, for our invitation and all.
Thank you so much for inviting me.
Yeah, madam. Okay, madam.
Okay.
Bye-bye.
Bye-bye.